Our next speaker is Savannah Gowen from Mount Holyoke College. Savannah has been working with me this summer on a collaborative project between Florida State, Gowen College, and an institute in Germany that's very difficult to pronounce. So I'll let you read it for yourself. The title of her talk is Searching for Intruder States in Arsenic 73.
Alright, so my name is Savannah Gowen, and I want to talk to you guys a little bit about navigating the Wild West, which I'll explain a little bit later, but most importantly, looking for intruder states in the nucleus arsenic 73. And before I jump in, I just want to give a little taste of why nuclear physics is cool and important. So nuclear weapons, nuclear power, you guys know a lot about that. Also, MRI technology came out of this field. And it's even believed that by studying the nucleus, we can learn more about how our universe developed. So lots of cool applications. So I'll just jump into the nucleus itself and the main model that we have for the nucleus, and that's the nuclear shell model, which is very similar to the atomic shell model that you guys are probably more familiar with. So in the atomic shell model, you have a nucleus. It's surrounded by these levels of increasing energy, or these shells, and you fill those with the electrons. So the nuclear shell model is different just because now we're filling our shells with protons and neutrons. Because of the strong forces that hold protons and neutrons together in the nucleus, we have a strong potential. And because this is a really small system, it's definitely a quantum mechanical system. And theoretically, we can derive some sort of wave function for that potential. It's a lot more difficult than it sounds, but over here on the right, I have just a diagram that shows those different energy. You get discrete energy bands when you do this calculation, and these are those discrete energy bands which make up these shells. And the circled numbers that you see correspond to the number of particles in a closed shell, or the number of particles that fills up a shell. So, okay, as these shells are filled up, there is a preferential configuration, and that is this pairing of protons with other protons and the pairing of neutrons with other neutrons. And what happens when you get that pairing is that the angular momentum of the two particles actually cancels out. So you can imagine when you have a nucleus that has an even number of both types of particle, it should have zero angular momentum. You can also then imagine that if you have an odd number of either one of the particles, it's that one particle that determines the behavior of the entire nucleus. And so what can happen when you start adding energy to a system like this is that single particle can be excited or promoted to a higher energy level, or you can break one of these proton-proton or neutron-neutron pairs such that the particle is excited to another energy level. Or thirdly, you can get a collective behavior in which all the particles are behaving together and you can get a collective rotation or vibration. So I want to take a look here at an image that I have that shows the nuclear landscape, or just all the known nuclei, and it also has this color component which corresponds to the amount of deformation in these nuclei. So these kind of evenly spaced incremented blue regions correspond to those closed shells that I mentioned, so nuclei that have that completed shell. And we basically know a lot about the behavior of those because they're so stable. Our models work well for these nuclei. But what we're interested in is looking at these nuclei that are a little bit off the beaten path. So in particular, I want to zoom into this region over here. It's very colorful. We've got the red, the greens, the yellows, and this is what we call the Wild West. And this particular region is characterized by the fact that for small changes in particle number, we get rapid changes in deformation and shape compared to regions with a much higher mass. And so it's in this region that arsenic 73 lives, and that I want to zoom into and investigate a little bit more. So there's a few features in particular that we're looking at in this region. The graph I have here shows energy versus deformation, and each of these dotted and solid lines correspond to an energy state that an individual proton or neutron could occupy. The circled numbers correspond to just the total number of protons or neutrons. So we're going to be looking at this lower mid-region because arsenic 73 has 33 protons and 40 neutrons. In particular, the majority of nuclei that are created are going to have single particles that occupy one of these states, this P, this F, and this other P. And they tend to have moderate deformation. But you'll notice sort of creeping into our region here, this guy in the corner, he sort of sneaks in there. And that is this F7 half state. And so this state is characterized by really high deformation. It sort of intrudes into our mass region, but this guy is really, really rare to find. It's hard to find, but we believe that it could be an occupied state in arsenic-73. And part of our evidence for that is that we've actually seen it in the neighboring nuclei, arsenic-71. So here is a level scheme for arsenic-71, which just organizes the energy levels and transitions. So these lines here are your energy levels. The arrows are the transitions between those as the nucleus relaxes to its ground state. And you'll notice over here, this 7 halves minus state. And to top that, we have a couple other energy states that are incremented approximately evenly. And this is great proof that this is the 7 halves minus state we're looking for, at least in arsenic-71. And that's because when you have a nucleus that's occupying a state with this much deformation, you know you're going to get a collective rotation. And so this sort of stacking ladder structure is a signature of that rotation. And this is what we're looking for in arsenic-73. So we didn't start empty-handed. We have a preliminary level scheme that was published by Raju. And part of my work this summer was just kind of verifying what we saw in this level scheme. But I also want to highlight these sort of nubs that come out over here that look like they could be really probable hosts for our 7 halves minus bands. So to start investigating this problem, we used data that was collected in an experiment run at Florida State University last summer, in which they took carbon-14 nuclei, accelerated them really fast, smashing them into nickel-62, and creating a new nucleus that can then either undergo a fast fission or create this really high-energy compound that's going to rotate, spew off particles, and one of the products of that is arsenic-73, which is then going to be created in some really high-energy state. It releases high-energy gamma rays as it relaxes to its ground state, much like an electron would release a photon of light as it's relaxing to its ground state. At Florida State, they have an array of germanium detectors, which then capture those gamma ray emissions, convert them into an electrical signal, and thus we can look at the gamma rays as a spectrum on our computer screen. This is just a characteristic look at what a spectrum will look like. And you'll notice that there's a ton of different peaks because we have so many different nuclei here. It's not just one at a time, it's not just arsenic-73, unfortunately. So our next big task is being able to filter that data so that we can actually get some useful results. And the main method that we have for doing that is called gamma-gamma coincidence. And so the idea behind a gamma ray coincidence is that a nucleus is produced about every 100 nanoseconds. And it takes much, much less than 100 nanoseconds for that nucleus to relax to its ground state. So you can imagine if I have a nucleus that's created in this energy state E3, within 100 nanoseconds, I shouldn't see a nucleus that is created in this energy state E4, which means if on my spectrum I see this gamma-3, I can use this gating technique to tell the electrons, okay, show me only the gamma rays that were emitted within the next 100 nanoseconds of gamma-3. I should see gamma-2 and gamma-1, but not gamma-4 because not enough time was allotted for that nucleus to have been created. And so this is just an example of how useful that method is. On top here I have a full spectrum. In particular, I want to look at this 609 transition that shows up in the arsenic-73 level scheme. It's right about here. And when I gate on this 912 transition, which is in coincidence with that 609, you can see how much more prominently my 609 peak stands out and how much of the noise is extenuated. So it's using this method that I was able to make a lot of different changes to the arsenic-73 level scheme this summer. My changes are highlighted here in red. I've added a couple energy levels, done a little switching around in order of a few transitions and a little deconstruction over here on the left side. Unfortunately, what you won't see here is that 7 halves minus band that we were really searching for. But we're hoping that as this project is continued in the fall that somebody can still find that. So our next step with making these changes was to verify that these make sense. And to do that, we used these energy levels and spin states that were amended here. And we calculated the moments of inertia for a given band in arsenic-73. and that is, arsenic 73 is highlighted here in red. And when we did that, we did that to compare it with the same values for the neighboring uneven nuclei, arsenic 71 and arsenic 69. And so you'll notice, just in general, we have the same sort of trend. We're going here, we have this bump up, and we're at higher energy level, we're at higher moments of inertia. And that this kind of pink here actually corresponds to one of those breaks in those pairs of protons and proton-proton pairs and neutron-neutron pairs. Also, you'll just notice these guys are around the same value, so this is a really promising and encouraging result. Lastly, we wanted to do a little bit of theory versus experiment comparison to sort of end off the summer. And so we used shell model calculations that were provided to us by Florida State and compared those predicted energy levels with our experimental energy levels. You'll notice that for the smaller energy levels, we get pretty good correspondence, and then that starts to decay as you get higher and higher. So that's what I did this summer. Lots of changes to be made and lots of work still to do. Just want to thank the NSF for funding me, Ohio Wesleyan, and my mentor, Professor Heron Kay, for a great summer.
Thank you, Savannah. Questions?
Do you have an idea of why the experimental results are significantly different from the shell model theory?
Yeah, I think the easiest answer for that is just that our theory isn't that great. And it's because it gets complicated when you have, especially in a quantum system like this, where you're looking at all these particles and their interactions on each other. So capturing that potential, and then just in general, the higher energy that you get, the longer it takes and the more complex the computations become. So we start getting more and more discord there.
The shell model calculations are attempting to describe the interactions outside of a closed nickel-56 core. So that's a many body problem. That's a tough one to solve. So.
Sounds like you need a quantum computer.
Be in touch. Other questions for Savannah? Huh?
So related to like the gamma coincidence measurement, so you said like it takes way less than 100 nanoseconds for a nucleus to relax to ground state. So can you, well, in principle, like make the window to be smaller and eliminate like more noise? You know, so that like the gating method would be better.
Yeah, you actually can do that. And actually, in our future, we're hoping that by narrowing our window, our time frame for that gating, it'll be easier to pick out that 7 halves minus band if it does exist. So that's up on the board in the future.
Of course, there's always a trade-off, right? You make that, you can cut out maybe more noise, but possibly, but then you probably reduce the counts.
What do you use to do like the level scheme, like the big?
Mathematica.
Okay.
There's a special program that we can use in Mathematica.
That's really cool.
Okay, let's thank Savannah again.